Here we're going to continue our first lecture of Chem 351. We're going to start off with the first law of thermodynamics, and this will be part 1. Lecture 2 will contain part 2 of first law of thermodynamics. As you may recall from introductory chemistry, there are 3 laws, law 1, 2, and 3, and we're going to start with the first law of thermodynamics. Okay, let's start out with a quote. Thermodynamics, this is, by the way, by Arnold Sommerfeld, who was a physical chemist back in the early 1900s. He said, "Thermodynamics is a funny subject. The first time you go through it, you don't understand it at all. The second time you go through it, you think you understand it except for 1 or 2 small points. And then the third time you go through it, you realize that you don't understand it at all. But by that time, you're so used to it that it doesn't bother you anymore." So this may be the first or second time you're going through thermodynamics, and it probably won't make as much sense. It won't be really cohesive this time, but if you keep studying it, eventually you get so used to it that those things that you don't understand don't make much difference because you know the lingo and just stalk your way through it. Thermodynamics is like brandy. They say you don't really appreciate brandy until you're over 60 years old. I'm over 60 years old, and I think the way that is that when you are actually drinking brandy, and you're over 60, your taste buds are shot, so that you don't really know that it doesn't taste very. Okay, let's go on to another quote. This is by Albert Einstein, who was a physicist again in the 1900s. He said, "Thermodynamics is the only physical theory of universal content, which I'm convinced that within the framework of applicability of its basic concepts, it will never be overthrown. And most scientists believe this. Thermodynamics is here to stay. If you look at thermodynamics, say 300 years from now, it'll still be valid." Of course, that's what they said about classical mechanics in the late 1800s, and along came quantum mechanics. But I think, at least in your lifetime, thermodynamics, the first 3 laws of thermodynamics, will always be held true. All right, so enough about quotes. Let's start with the first law of thermodynamics. Here are 3 statements, 3 qualitative statements of the first law of thermodynamics. Let's look at the first one. The energy of the universe is constant. That's a statement of the first law of thermodynamics. And so let's sort of get an ink color here, white. Let's go back to the previous lecture, lecture 1a, where we define the universe as a big box. And here's the universe. And within the universe, the energy is constant. That's the statement of the first law of thermodynamics. Within this statement, we're assuming that the universe is a closed system. In other words, what we're saying is that there can be no energy flow back and forth between them. Well, that sort of makes sense. If the universe is everything we know, then where's this energy going to or coming from? So that's a pretty good assumption. The universe is a closed system. There's no energy going in and out of it. So within this universe, energy is a constant. Now, when the universe was created, however it was created with a constant amount of energy. That's all it has, and as time went on and the universe evolved, here we are at present time. The universe has the same energy now as it did at the very beginning of the universe. The energy of the universe is a constant, and that's the first law of thermodynamics. One statement of it. Here's another statement. The energy of an isolated system is constant. And what's an isolated system? There are no energy flows between the system and surroundings. So that's what we said here. The universe is an isolated system. It's a closed system, but we can also say it's an isolated system. So an isolated system, no energy flow. So let's draw another universe down here. Actually, it's the same universe. There's presumably only one universe. And within that, we're going to draw, as we said in the lecture before, a system here. And we said that the part of the universe, so this is the universe, the part of the universe that's not the system is the surroundings. And energy can flow from the system to surroundings. The total energy within the system plus surroundings has to be constant. So if you take a certain amount of energy from the system and put in the surroundings gain just as much energy as the system had. So another way to say this is the energy of the system plus the energy of the surroundings has to equal 0 in general. Okay, and that also means that the change in energy of the universe has to equal 0, because if there were a change in the energy of the universe, then the energy of the universe would not be constant. All right, so now here's yet a third universe, same universe as before. And what we're going to do here is to draw our system within the universe, and this would be an isolated system. So isolated system, we said energy cannot flow between the system and the surroundings, and this is the universe. So since energy cannot flow, if you look at this isolated system, this sort of mini universe in here, we say that the change in energy of the isolated system has to equal 0. So that's what we mean when we say that the energy of an isolated system is a constant. So not only is the universe isolated, but if we carve out a particular part of the universe and make it isolated, insulated, so no heat can flow, make it rigid, and all that stuff, then no energy flow between the systems and surroundings, then the energy of that isolated system is a constant. And then a third statement of the first law of thermodynamics is energy is not created nor destroyed. Energy, however, can be changed from one form to another, and we'll see on the next slide here what two major energy forms are. Or energy can be moved from one place to another. So, for example, here we're taking energy, we move one place to another, and that's okay as long as how much we move from one place is equal to how much we put in the other place. Or another way of stating that is that energy can be changed from one form to another as long as the total energy remains constant. So for example, in the next slide we'll have heat and work. You can change a certain amount of heat into work, but the energy heat, that amount of heat has to equal the amount of work that's gained, again for an isolated system. All right, so I hope you have a pretty good qualitative understanding of the first law of thermodynamics. We'll now go on and talk about our first equation in physical chemistry. Here it is. It's another statement of the first law of thermodynamics. All right, let's go up here first. Engineers back in the middle and late 1800s decided to divide energy into two different types. One was heat, and that's defined as energy flow in response to a temperature gradient, and then work, that was all the other kinds of energy. All right, so let's go back to our previous lecture. Let's look at a temperature gradient. So here we have temperature, and here we have x. And remember, gradient is a derivative of something with respect to some spatial coordinate. Here we're just doing one dimension, x. And let's say at this particular point in x, we have this particular temperature, and at another position, we have that particular temperature. This means that there's a gradient in temperature. Now, if we have heat here, or actually what happens is that energy flows in the form of heat from a high temperature to a low temperature gradient. If we look at a more concrete example, suppose we have two metal blocks, and here this is at high temperature, and then right next to it we put a the same kind of metal, but now here we have low temperature metal block. So here we have a temperature gradient. At this particular point in space, we have a high temperature. Here we have a low temperature. What will happen is heat will go from the high temperature to low temperature, and our everyday experience says that the temperatures will eventually equalize. This is getting into the second law of thermodynamics. So heat can be thought of as a flow of energy in response to a temperature gradient. And as we'll learn when we talk about the second law of thermodynamics, we really shouldn't be talking about Q. The natural variable that goes with T is entropy S. Okay, so that's what heat is. And then the engineers said, well, everything else we'll call work. So the total energy can be divided into two parts, heat and work. Now, the first law of thermodynamics says that du is dq plus dw, where u is the internal energy. That's the energy of a system, internal energy. Q is heat, and w is work. All right, so du is dq plus dw. Now, let's take a digression and talk about this symbol d. What does d mean? Well, that's a differential. Let's go back, review a little bit of calculus. Suppose you have a function of a single variable. So this is f of x. An example of this might be f of x is equal to mx plus b. That's an example. When you put in a certain value of x, you can calculate the function f of x. This is sometimes called y. Y is equal to mx plus b. This is the linear function. Let's take 2 points here. Let's take this point. This will be x1, and this will be f of x1. And let's take this point down here at x2, and this will be the value of that function at x2. If you're into experimental stuff, this is the independent variable here, and this is the dependent variable here. And now let's look at the slope. The slope here is equal to delta f of x divided by delta x, where delta here is always defined as the final minus initial. All right, so let's call this the final. We use the number 2 for final. And let's call this initial. So the slope will just be f of x2, the final value, f of x2, minus f of x1, divided by x2 minus x1. All right, now what we want to do, note that these are deltas. We want delta to approach 0. All right, so now what do? All right, what we do is we move these points closer and closer together until they're as close as possible. The distance between these points, in fact, will be 1 over infinity. Well, you have to take limits and so on, but in calculus, what you do is that these points, when they approach one another, they get infinitesimally small. So now you have a point here and a point here. And then we have here. This was Isaac Newton's idea, by the way, in the 1700s. He invented calculus to explain celestial motion. Now, delta has gone to the symbol d. So d means you have a difference, and the difference is infinitesimally small. All right, so infinitesimally means 1 over infinity, and that's essentially 0, but you have to take the limit. So there really is a space between them, but it's infinitesimally small between these 2 points. Now you write the slope is, instead of delta fx over delta x, it's d fx over dx. So that's when this difference here is really, really small. That's what the slope is. All right, so d is an infinitesimal difference. It's a differential. So when you go back here, this says the differential change in u is equal to differential change in q plus a differential change in w. All right, so let's apply that. Here's again is our universe. That universe is coming in handy, and within the universe is the system. And this is the system. So what you can do is have some incremental change in the two forms of energy, du and dw. And here's the system, du. Remember, U is a symbol for internal energy, energy of the system. So that the change in the internal energy is how much heat you put in or taken out of the system, and how much work you've done on, or the system did on, the surroundings. Again, this is the surroundings. So another statement, or the quantitative statement of the first law of thermodynamics, is that the change in the internal energy of a system is equal to dq plus dw. So how much the energy is how much heat you put in or take out, and how much, that's w, and how much work you do, or how much a system does work on the surroundings. And that's when it makes sense. That's how the energy is changing. You're putting energy from the surroundings, or taking it from the surroundings. You're putting energy from the surroundings, you're taking it from the surroundings. And we've artificially divided total energy into heat and work, since we're living probably in the 1850s, where the engineers decided to do that. Okay, so there it is. Well, this is interesting. Suppose that you have an isolated system. What will du be for an isolated system? Well, remember, for an isolated system, you can't have any energy transfer. So there'll be no heat transferred, no work transferred. So du will be equal to 0. And so any change in energy will dw. This means that the change in heat will be equal to minus a change in w for an isolated system. All right, so du, that's just essentially a change in energy, but the change is infinitesimally small. That's what the d, infinitesimally small change in q, infinitesimally small change in w. And let me rewrite that there. Eraser, yes, the eraser is kind of cool. Eraser function, dw. There we go. So I hope you have some understanding here of what this differential form of the first law of thermodynamics means. So it makes sense. The only way you can increase the energy of a system is to first of all have a non-isolated system, and then stick in some Q from the surroundings, or W from the surroundings, or vice versa. All right, first law of thermodynamics. Now, let's write another form, the integrated form of the first law of thermodynamics. Delta U is Q plus W. So what we're going to do is take this differential form of the first law of thermodynamics and integrate it. So let's integrate the left side, du. Okay, so integrate that, and we'll do definite integral from the initial u1 to the final u2 du. And I hope you remember from calculus, essentially we're integrating 1. That is equal to u2 minus u1. And remember, this was the final state. This was the initial state. So we can write final minus initial, use the symbol delta. So this is just delta U. All right, good. Now let's integrate okay, go this way. I integrate the right-hand side of the differential form of the first law of thermodynamics. Okay, so let's integrate from Q1 to Q2 of dQ. Now, this is going to be a problem. This you can do because U is an exact differential. So we could get a delta U here. dQ, on the other hand, is an inexact differential. What does that mean? Exact differential implies the integral does not depend on path. In other words, going from the initial state here to the final state here, doesn't matter which way you go. So here you have U1, here you have U2. You can go this way, you can go some other path, you can go some other path. Delta U is a constant. No matter which path you go, you get the same delta U. An inexact differential implies that the integral does depend on path. So, for instance, if you go from the initial state to a final state, actually this is technically incorrect. If somebody, say a calculus teacher, were looking at this, he or she would cringe. But just let me say this is the initial, and this is the final. All right, so the initial to final state depends on which way you go. It's an inexact differential. So it's really not a delta. That's why we put Q here. Q is the amount of heat transferred, which depends on how you go from one place to another. How do we know that it depends on path? Well, experience tells us that. And similarly, if we go from the initial to the final state of dW, dW also is an inexact differential. So it depends on path. So here we have to write W. That's the total amount of work done in going from the initial state to the final state. And that total amount of work done depends upon the path you go from the initial to final. In contrast, internal energy is inexact differential. The integral does not depend upon path. Okay, so that's the integrated form, two different forms of the first law, the differential form and the integrated form. Now, remember from introductory chemistry, internal energy U is a state function, and W and Q are not. What's the definition of a state function? State function from introductory chemistry. A state function means that does the change, delta, does not depend on path. And, well, we already know that that means that the function is an exact differential. So now we've taken what we learned in introductory chemistry and now built upon that. That's a lot of what chemistry is. You learn something and you think you know it, and then you go to another course, advanced course, and then, yeah, you knew it, but you didn't know the whole story. Well, here's the whole story, and we'll get even more of the whole story when we talk about Maxwell's relations and more information about exact differentials. So state function, that means that U is a state function, and W and Q are not state functions. They depend upon how you go from the initial to final state. Therefore, they're inexact differentials, and you can't write just a one initial or final minus initial for that. So, as we said, the engineers divided energy in terms of heat and work, and let's look at some examples of work. One is muscle contraction. There, work is done as your muscles, say you're pulling on something and you move it a certain distance and you apply a certain force with your muscle. To figure out how much work you did, you multiply force times length. Let's look at engines, say an internal combustion engine. What you do is you burn some gasoline, and that increases the pressure in a piston, and that piston is pushed down, the volume is decreased, so it's a pressure times volume. And that's how much PV work, pressure volume work, an engine does. Here's a new concept probably. It turns out that chemicals have chemical potential. And that is, for instance, in a chemical reaction, you got reactants and products. As the reactants go to products, the reactants have some chemical potential and high chemical potential, and as they go to products, they go to lower chemical potential, and so molecules, a number of molecules more precisely, would be the what is changing here. So you got potential and chemical in number of molecules. And you might remember from the last lecture, these are natural variable pairs. You got an extensive and intensive variable. Force and length are natural. You multiply them together, you get energy, which the engineers have said that's going to call that work. Same way here, pressure and volume. They're two natural variables, an intensive and extensive variable, and you multiply them together, you get energy or work. And finally, we'll learn more about this later on in the course. You have chemical potential and number of molecules, and you multiply these two together, you get energy or work. All right, so that's the first part of the first law of thermodynamics. Be sure if you have questions, bring them to the first lecture, which is Wednesday of the first week of classes. Okay, thanks.